Welcome back to this video in the proof by induction series. So here we're going to look at using mathematical induction to prove a general term of a recurrence relation. Now, these you saw back in P2, or if you're doing this alongside your regular maths, you might have done it right now, but you could just be doing this alongside alongside P1 at the moment. So in which case you'll see these when you get to P2. But what it is a recurrence relation is like for sequences, and it produces sequences based on the previous term. So for example, you could have u of n plus 1 is equal to 5u of n minus 1. And that might be when n is greater than or equal to 1, because the first term is n equals 1, second term is n equals 2, so can't be any lower than that. And then they usually have to give you what the first term is. So in this case I'll call it 3. Okay, and then you substitute that in. So u1 is 3, u2 is 5 times u1 minus 1. So 5 times 3 minus 1, which is 14. And then u3 is 5 times u2 minus 1, or 5 times 14 minus 1, which equals 69. And so on. Okay, and sometimes you see these with a u n plus 2, and then in here will be a u n plus 1 and a u n, and then they have to give you 2 terms. Okay, so this is the recurrence relation, and it produces our sequences. And what we're going to do now is use a mathematical induction to prove like this recurrence relation here. And then if we're given the nth term of this sequence, okay, obviously this is a bit of a weird sequence, but if we're given the nth term of the sequence, we can then prove that that is the general term. So it's basically a proof from proving that another statement, another rule is correct. So using basically the difference between the recurrence relation, which is this, and then the nth term, okay, which is the general term. Okay, so that's what it is. It's not too difficult, but let's have a look at the first example and you can decide for yourselves. So here we have our first example. So here's our recurrence relation. It's here with u1 being the first term being 4, and proved by mathematical induction. That should be that. I'll change that in a moment. un is 5 to the power n minus 1. Okay, now it's the same 4 basic steps. Okay, the basis step, the assumption step, the inductive step, and the conclusion step. So first we're going to look at the basis step. So that is when n equals 1, and it's the same for all of them. So for that we substitute in to our general term here. So u1 is 5 to the power 1 minus 1, which is 4. And that is clearly the first term here. So as given. But now we go to n equals 2. So for this, so we go u2, so this is 5 squared minus 1, or 24. And this is from the general statement. You may be able to hear a little dog in the background now and again. That's my puppy, who isn't making it easy to make these videos. Okay. Now, when I've done that, I also need to put it into the recurrence relation. So u2 into the recurrence relation is 5 times u1 plus 4. So that is 5 times 4 plus 4, which is 24. And that comes from the recurrence relation. So now we've shown it's true for n equals 1 and n equals 2. So we can state that. So un is true for, or when, it's maybe a better word, when n equals 1 and n equals 2. So now we've done that, we can assume, so that's our basis step done, okay? So now, yeah, our assumption step, so we assume that for n equals k is basically true. So assume, sorry, I wrote that incredibly small. There we are. Assume that for n equals k, uk equals 5 to the power k minus 1 is true for k, and that's an element of the positive integers. Then we move on to the inductive step. Okay, so in this step we are using k plus 1. So u of k plus 1. Okay. Now this is going to be the recurrence relation. So that is 5u of k plus 4. Now for u of k, we're going to substitute this in. So this becomes 5 times 5k minus 1 plus 4. So 5 times 5k is 5k plus 1. Remember this, that's 5 times 5 to the power k. This is the power 1, and we add the powers, don't we? Okay, so that is that one. Minus 5 plus 4. So 5 to the power k plus 1 minus 1. And you can see that this now resembles this, but when n is k plus 1. So we've started with u of k plus 1 of the recurrence relation. We substituted our assumption in for the general term, and then we've shown that we get the general term for k plus 1. So therefore the general statement un is true when n equals k plus 1. Now, all we've got left to do now is our conclusion. And as I said before, and as you probably noticed, when I'm writing lots of things, I find it hard to write and talk at the same time and try and spell. And that's my biggest problem, is me trying to spell. So I'll just speed the next little bit up of me writing, and then we'll discuss. And there we have the conclusion. So if n is true when n equals k, then it has been shown true when n equals k plus 1. As un is true for n equals 1 and n equals 2, then it is true for n greater than or equal to 1 and all positive integers of n by mathematical induction. Okay, so that's how we do one of these examples. Now, when we have one when it's a u n plus 2, then we have to do n equals 1, n equals 2, and n equals 3. Okay, so we have to take that extra step then. Okay, and that's just because n equals 1 and n equals 2 will be the first two given to us. So if this is n plus 2, we'd have a u1 and a u2. So we do the first two that are given to us and then one additional one. Okay, so like in this one, we do the first one, which is given to us, and one additional one. In fact, let me do a second example with a u of n plus 2. Okay, second example. So we're doing one with an n plus 2. Here it is. Because we've got an n plus 2, we've given u1 and u2 in this case. Okay, proved by mathematical induction that un equals this. So same kind of start as the last time. So we start with n equals 1. So we're going to do u of 1. Okay, now this is 1 minus 2 times by 3 to the power 1 minus 1. So 1 minus 2 is minus 1, times by 1 is minus 1. So that is my n equals 1. Now we move on to n equals 2. 2 minus 2 times by 3, 2 minus 1. 2 minus 2 is 0. Anything times by 0 is 0. So these are both now as given. Because the answers are given in the question. Now we move on to n equals 3. So that one extra one. And first we do the general term. So 3 minus 2 times by 3 to the power 3 minus 1. So 3 minus 2 is 1 times by 3 to the power 2, which is 9. So n3 is equal to 9, and this is from the general statement. Now next we do it from the recurrence relation. So u3, it's u of when n is 1 really, because 1 plus 2. So that is 6u of 2 minus 9 times u of 1. So it's 6 times minus 1 minus 9 times 0. No, sorry, done that the wrong way around. Let me rub that out. u2 is 0, isn't it? So 6 times 0 minus 9 times minus 1. So 6 times 0 is 0, minus 9 times minus 1 is 9. And this is from the recurrence relation. So from recurrence relation. Okay, and we can see that they are both the same. Okay, so UN is true when n equals 1 and n equals 2, and also when n equals 3. Okay, so that's my basis step. Slightly different to last time. I had to do that extra value of n. But now I can go on to my assumption step. So assume. So we're assuming true now for n equals k. So assume that for n equals k and for n equals k plus 1, okay, both. So we've got UK is going to be k minus 2 times by 3k minus 1, and UK plus 1 was k plus 1 minus 2 times by 3k plus 1 minus 1. This is k minus 1 and 3 to the power k there. I don't know whether to, simplify it now or whether it's, we will need the original later, but I'll go ahead and do that for now. So that now is my assumption step. So now I come on to the inductive step. Okay, now the inductive step in this case, then we're looking at u of k plus 2. Now that is because we had the n plus 2 up there. So you see the slight variations now in this example compared to the previous example. So this is 6u k plus 1 minus 9u of k, and then we substitute in our assumptions. So this one and this one. So that's 6 times k minus 2, 3 to the k minus 1, minus 9 times k minus 1, 3 to the k. Okay. Sorry, I've got these the wrong way round. So it's 6 times k plus 1, so this is 6 times k minus 1, 3 to the k, minus 9, k minus 2, 3 to the k minus 1. Almost a big mistake then. Now, this k minus 1, or 3 to the k minus 1, 3 to the k minus 1 is the same as 3 to the k times by 1 over 3, isn't it? Because it's 3 to the k times 3 to the minus 1, which is a third. Okay, now down here I've got a 9 in front. So what I can do is I can replace this with this, and the third times 9 is going to give me 3. So this is going to be 6k minus 1, 3 to the k, minus 3k minus 2, 3 to the k. Okay, so that now makes it a little bit easier to deal with this expression. Now I've just moved this just from here underneath, just gives me a little bit of room to carry on writing up here. So this is u to the k plus 2. Now I can factorize out my 3 to the k, and that leaves me with 6k minus 6 minus 3k plus 6. Yeah, from expanding these parts. So taking the 3 to the k out, and I got 6k minus 6 minus 3k, and minus 3 times minus 2 is plus 6. So this now leaves me with 3k multiplied by 3k, which is k. Now if I take the 3 out, so 3k times by 3 to the 1 is 3 to the k plus 1. So if I take this 3 out, it'll be like this, which will be like this. So that means that it's just k multiplied by 3 to the k plus 1. Now, this means we got k plus 2 minus 2 times by 3 to the k plus 2 minus 1. Okay, so this is just replacing this k plus 1. So this is still k plus 1, because k plus 2 take away 1 is k plus 1. And this is still k plus 0, k plus 2 minus 2. And the reason we're looking for that is we're looking for that k plus 2, that k plus 2 there. Okay, which matches up to this. Now, when n is k plus 2, we got k plus 2 minus 2, which is here, and 3 to the power k plus 2 minus 1, k plus 2 minus 1. So we've now shown that it's true for mathematical induction. Okay, so there we can stay. So this is the same expression that the general statement gives for u of k plus, sorry, I went to write k plus 1 there, for u of k plus 2. Therefore, the general statement is true for n equals k plus 2. General is true for n equals k plus 2. Now, all that's left to do now is my final step, which is the conclusion. Whew, just about squeezed that in there. So that's the conclusion. Learn the conclusion, learn how to write it. It's pretty self-explanatory. Once you've written a few of them, you'll be golden. Now, don't forget, when you're practicing these, don't, practice it all and then just say, right, I'll skip the conclusion because that's pretty much the same every time. And I'll just remember it, later to the date. Don't. Keep writing the conclusion every time. Once you've done 6, 7, 8 of these, you'll have the conclusion, pretty much memorized. So all that's left now is to practice a few questions yourself. But before you do, don't forget, if you found this video useful, you might not enjoy it. Not everyone enjoys everything in maths, but if you found it useful, helpful, don't forget to hit that like button. If you are not a subscriber, hit that subscribe button. Obviously it's free. It does help me out, and it helps you, see my latest videos and see videos that might be of use to you. And if you have been watching the channel for a while and you want to give a little back to me, then please consider hitting that join button. You know, even if it's only for a month, every little bit helps. If everyone who watches these videos joined for just 1 month, that would massively help me out and enable me to make more videos in the future. So anyway, let's look at the questions. So here we have 2 questions. I'm not going to do any more because the proof by induction, it's quite time consuming and it's not too difficult. So I'm just going to do 2 questions. Once you've had a go at these, then don't forget to have a go at a few more yourself. Use your textbooks, use online, use ChatGPT to create some questions for you. But make sure you probably do 5 or 6 questions to make sure you are, you know, completely comfortable with this. Okay, so don't forget to pause the video now. And then now we look at the answers. Okay, so n equals 1/5 of all. And we've got to show that u1 equals 5 to the power 1 minus 1 plus 2. So 5 to the power 0 is 1 plus 2 is 3. So that is as given in the question. Then we go one more. So u2, that's 2 minus 1 plus 2. So that's 5 plus 2, which is 7. Okay, and that's from the general statement. Okay, then we do the other one, u2 from the recurrence relation. So that is 5 times u1 minus 8. So 5 times 3 minus 8, which is 15 minus 8, which is 7. And this is from the recurrence relation. Okay, so I've done the first 2 here. So now we can make a statement. So un is true when n equals 1 and also true when n equals 2. Now my assumption, so assume that for n equals k, and we've got uk equals 5 to the k minus 1 plus 2. And we're assuming that is true for all of k. K being an element of positive integers there. Now we're going on to the inductive part. So then u of k plus 1 is going to be 5u of k minus 8. And substitute in for uk. So it's 5k minus 1 plus 2 minus 8. So 5k minus 1 times by 5 is going to be 5 to the k plus 10 minus 8. So it's going to be 5 to the k plus 2. Or 5 to the k plus 1 minus 1 plus 2. And then we have it in this form, k plus 1 minus 1, which is just k, plus 2. So therefore, the general statement un is true when n equals k plus 1. Okay, and then finally our conclusion. So if now I'll just speed this little bit up. Okay, so that's the first question done. Let's have a look at the second one. Okay, so n equals 1 first of all. So u1 is 2 to the power 5, 1 minus 1, minus 2 to the power 1 minus 1, which is 2 times 1 minus 1. So 2 times 1 minus 1 is 1. N equals 2. So u2 is 2 to 5 to the power 2 minus 1 minus 2 to the power 2 minus 1. So that's 2 times 5 minus 2. So that's going to be 8. So both of these are as given. Okay, as given. Now we need to do that extra 1. So n equals 3. So carry on with the, the general term first, since I've been doing that one. So we got 2 times 25 minus 4. So 50 minus 4, we get 46. And this is general statement, isn't it? I couldn't think of the word then. And then we got to go u3, and now this is from the recurrence relation. So 7u 2 minus 10u1. So 7 times now u2 is 8 minus 10 times u1 is 1. So this is 7 times 8, which is 56 minus 10, 46. And this is from the recurrence relation. Okay, so that now we've shown is true. Okay, now we make the assumption. So we're assuming now. So we're assuming UK is 2 times 5 to the power k minus 1 minus 2 to the power k minus 1, and UK plus 1 is 2 times 5 to the power k plus 1 minus 1 minus 2 to the power k plus 1 minus 1, or 2 to the power 2 times 5 to the power k minus 2 to the power k. So those are our things, and they are true. Oh God, what kind of writing is that? So are true for k being an element of the positive integers. Now the induction step. So this time we're looking at k plus. So this is 7 u of k plus 1 minus 10 u of k. Now I need to make sure I write the right ones in this time. So 7 times 2 times 5 to the k minus 2 to the k minus 10 times, and it's 2, 5 to the k minus 1 minus 2 to the k minus 1. Now I need to kind of go ahead and sort this out. So I've got 14 times 5k minus 7 times 2k minus 20 times 5 to the k minus 1 minus 10 times 2 to the k minus 1. Okay, now let's get my 5 to the powers together, and also let's sort out these with the minus ones. So that minus 1 there is going to be like 5 to the k divided by 5. So this is going to become 4, and this one will be divided by 2. So k minus 1. So take the minus 1 out, that'll be divided by 2. So I've got 14 5 to the k minus 7 times 2 to the k minus 4 times 5 to the k minus 5 times 2 to the k. So this now gives me 10 times 5 to the k minus 2 times 2 to the k. Now we had 2 outside of our 5 to the power, so I'm just going to bring that 2 out, and then we got 5 times 5 to the k minus 2 times 2 to the k. Now 5 times 5 to the k is 5 to the k plus 1. And 2 times 2 to the k is 2 to the k plus 1. So now we've got it basically in this form, but I want to just change that n to a k plus 2, isn't it? So that n to a k plus 2. And that's what we have here. So this is equivalent to 5 to the k plus 2 minus 1. Minus 2 to the k plus 2 minus 1. Now 2 minus 1 gives me that plus 1 that is here, and now this resembles exactly this, where n equals k plus 2. So we can say at this point, you know, therefore the general statement un is true when n equals k plus 2. And then finally our conclusion. Now I'm not going to write the conclusion because, you know, I've written it before. See the second example for how to write the conclusion for a n equal of for an n equals for a u of n plus 2 proof. Okay, but yeah, that's done. Hopefully you got those 2 questions out. You're ready to go ahead and try a few more. Don't forget, you know, you can use AI in a positive way to give you questions and answers, so more questions to try and the answers or the solutions to the problems, so that you can see, you know, where you went wrong. Okay, so it's very useful in that regards. Now for this, for FP1 course, we've just got one more video proving statements involving matrices. So I'm going to get that done coming up in the next couple of days, and then FP1 course is complete. Don't forget, like, subscribe, and see you next time.